Hello, on behalf of NDVI, I'm pleased to welcome you to this afternoon's webinar, Precision Agriculture in the Drone Age. My name is Katie Cooper, and I'm the Education Associate at NDVI and host of today's webinar. Before we get started, I have a few housekeeping items to note. NDVI's annual trade show, Exponential, will be held in Dallas this year from May 8th to 11th. We're excited to announce that Jim Cantori, one of the most recognized faces in weather broadcasting, will be our host. Jim will be joined on stage by Intel CEO Brian Krzanich and many other exciting keynote speakers. Registration is now open for our next webinar, FAA Tips for Receiving a Part 107 waiver, which is scheduled for Monday, December 12th. Be sure to check out aviasi.org for the complete 2017 webinar schedule. These programs are a fantastic way to continue the conversation and learn more about unmanned capabilities. I'd like to take a moment now to thank MicroSense for sponsoring today's event. We have an excellent program in store for you this afternoon as we delve into the use of drones in agriculture and the benefits for farmers. Today's webinar is being recorded and all participant lines will be muted during the broadcast. A recording of the program and the slides will be emailed to all attendees and posted to aevsi.org. If you're listening to the broadcast and need assistance, please send a note to AEVSI support using the chat box on the right side of your screen. After the presentations, I'll open it up for Q&A. You can submit questions throughout the webinar using the Q&A box on the right side of your screen. I'm pleased now to introduce today's speaker, Alyssa Ryan. Alyssa is the Customer Engagement Manager at MicroSense. Her goal is to educate customers about MicroSense's products and how they can be used to optimize their applications. Before joining MicroSense, Alyssa was a GIS analyst at Google Maps, where she worked to improve policy and mapping policy and operations for customers. Alyssa holds a bachelor's degree in urban planning and sustainable design from Western Washington University. So at this time, Alyssa, I'm going to pass control of the presentation to you, but will you do a quick audio check for us so we can hear you, make sure we can hear you?
Yes, can you hear me?
Yep, sounds good, all yours.
Great. Thank you so much for that introduction, Katie. I really appreciate it. I want to welcome you all here today. I'm going to talk a little bit more about drone-based sensors, specifically multispectral imagery, and how that is changing the way that we do agriculture. Before we get started, I'm going to do a brief introduction. The MicroSense team is made up of engineers, agronomists, GIS analysts, and people passionate about customer success. We really strive to bring high-quality science to the everyday user, and are doing this through the way that we create our products and through the way that we promote our educational material and share resources. MicroSense as a company produces professional multispectral sensors, as well as the data and analytics platforms that go along with those sensors. Our flagship product is the MicroSense Red Edge, which is a 5-band multispectral sensor that is calibrated and primed to detect changes in crop health through multispectral imagery. Atlas is our data and analytics platform, and it specifically works with the data from Red Edge to, like I mentioned before, bring high-quality science to the everyday user. We want to integrate our products in such a way that science is prominent throughout, and repeatability is especially high quality that we want to highlight. So before I get into the presentation, I want to give some context about the unique climate that we're in, specifically with regards to agriculture and UAVs. These are general numbers. They change from day to day, as I'm sure a lot of you know. These are numbers that we pulled, and again, they could change, but give a general idea of the market as a whole. Right now, the projected world population is 9.6 billion people by 2050. Agriculture production to feed all those people needs to increase by 70%. We need to make very significant changes in how efficient and how effective the agricultural production is. This is where UAVs come into play. Recent regulations, the lifting of recent regulations has really brought more UAVs to commercial industries, and we can leverage this in a way to help agricultural production become more effective and efficient. Overall, the agricultural drone market is expected to be worth $3.69 billion by 2022, which again contributes to that overall climate and unique position that we find ourselves in at this moment. Getting a little bit more into the details here, agriculture touches all corners of the world, and agricultural production needs to change throughout all corners of the world. The US and European markets right now are predicted to be the largest potential markets for commercial drones. We have seen a significant shift in the past 2 years from the focus on drone technology to the focus on sensors and data that those sensors produced. Right now, drone-based sensors are estimated to hold 40% of the agricultural drone market share. And again, this goes back to the overall message of we are in a very unique climate, and we have a very unique opportunity to leverage this technology to, again, make agriculture more efficient and more sustainable and more effective. So I'm going to talk a little bit more about remote sensing and precision agriculture, how remote sensing is used in precision agriculture. Remote sensing is a term that everybody should start to get used to. It is the science of obtaining information about objects or areas from a distance. It was traditionally done on satellites, specifically agricultural remote sensing. Satellites have been giving farmers NDVI maps. NDVI is something we'll talk about later in the presentation, but satellites have been giving farmers NDVI maps for years. And now, with the UAV market expanding in the way that it is, we now have an opportunity to change the way that this remote sensing is being done and you start to use drones. You can see remote sensing is primarily targeting light and measuring the reflected energy or light off of objects, props, et cetera, et cetera. As I mentioned, remote sensing has been traditionally done with satellites. However, with UAS, we get some key benefits. There's sub-meter resolution in a lot of drone-based sensors now. For instance, with a satellite, an agricultural satellite that's giving an NDVI map, you have 1 pixel of an image that could translate to 50 meters on the ground or 20 meters on the ground. With UAVs, specifically with the multispectral sensor that we make, at 400 feet, you can get, as it says there, sub-meter resolution, which translates even to as low as 8 centimeters per pixel. So 1 pixel of an image translates to 8 centimeters per pixel on the ground. In addition, you also can have more frequent data acquisition. You don't have to wait for a satellite to fly over a farm or a field to capture data. You can do this, on a daily, weekly, monthly basis, depending on the needs. It's also at a lower cost to deploy a drone than deploy a satellite. And again, as I mentioned, the limitations are lifting for agricultural remote sensing. While last year farmers had, or drone-based service providers, anyone operating a drone, had to apply for a 333 exemption. Now we have something called Part 107, and that gives people a much easier way to legally fly a UAV and legally operate a drone business. Something else that's really important to remember throughout the rest of this presentation is that remote sensing is one tool in a farmer's wheelhouse. It is not the miracle end-all be-all solution. It plays in fertilization, seeding, soil treatment, everything that you see here. It helps inform these decisions, but again, it's not something that should be solely relied upon, and that's something that we as a company really want to make clear. Farmers need to leverage this data and the imagery in a way that's complementary to the rest of their farming management practices. Okay, so now I'm going to dive a little bit deeper into the tools that go into agricultural remote sensing, specifically multispectral imagery. So before we talk about the actual tools, I give a little bit of the basic overview of what multispectral imagery is and what it does. So this graphic is meant to, again, be a little bit more detailed in comparison with the one about remote sensing that you saw earlier. As you can see, sun shines down on crops or plants, and it casts light in the full light spectrum, both visible and non-visible. Something really key there is the amount of light that's casted down in near infrared. That's specifically what we're concerned with, and I'll talk about that in a second. But once light is cast down upon plants, plants either absorb the light, they transmit the light to the soil, or they reflect the light back up. And that's specifically what we are interested in, is the amount that is reflected. That's what multispectral imagery measures. So in the graphic, you see that plants actually reflect a lot more near-infrared light than they do visible light. And so in near-infrared, actually, if you see a picture of a plant in near-infrared, you see it as looking very, very bright. So a lot of analysis for multispectral imaging is based on ratios with comparing near-infrared imagery as well. Taking it one step further, as you can see, you've got a graph that shows a typical plant reflectance on the left-hand side, and then the entire wavelength or spectrum on the bottom. And those color blocks, the blue, green, red, red edge, and near-infrared, are depicting filters that essentially only measure light in certain areas or certain wavelengths. These are actually the filters that we use specifically on the MicaSense red edge. As you can also see, healthy plant versus a stressed plant will reflect different amounts of light in different wavelengths. They reflect the most light in near infrared and, as you can see, in green, which is why a lot of plants look green. So before we move on, I want to make sure to stress that reflectance is a physical characteristic of a plant. It's something that is physically measured and is not just an image. We're not just taking pictures here. Healthy versus non-healthy plants reflect different amounts of light, and that's what multispectral imagery measures. It measures the difference. By analyzing that difference and by analyzing multispectral imagery or data, we can really determine how healthy a plant is and how healthy a crop is. Sorry about that. To get into multispectral cameras, we're going to talk a little bit about how a narrower band means that a camera is more precise. And when I say band, I mean a narrower amount or a smaller amount of wavelengths that a camera detects. We're also going to talk about how calibrated data is very, very important. It allows for time analysis. And also, we're going to talk about how calibrated cameras and narrowband cameras allow for the generation of advanced vegetation indices and analytics. Vegetation indices that, like I said, go beyond NDVI. So here is a comparison between a single imager camera or a specifically named NDVI camera and a narrowband multispectral camera. As you can see, the bands or the amount of wavelengths that the single imager camera detects a little bit wider, right? And when you do any type of analysis, you have to average the values that are in that band. And that means that the data overall is less precise. When you compare that to the narrowband multispectral camera, you see that the bands on the narrowband camera are much more precise and are at targeted areas of the curve. When we do, like I keep mentioning, NDVI, we're essentially taking a ratio between the near infrared and the red values of that curve. With a narrowband multispectral camera, you have more options available to you because you can do NDVI, but you can also do analysis that takes into account the green band, the values in the blue band, the values in the red edge band. This is a comparison of 3 different types of data. You can see an RGB data layer at the top, an NDVI map in that lower left-hand corner, and that shows some variation, and it's very valuable in giving you kind of an overall depiction of stress. But with the narrowband camera, you see so much more variation, and you can actually, again, use different analysis tools. The one shown here is particularly a chlorophyll map that I'll talk about a little bit in the future. But the point is that NDVI is great. Cameras that can do NDVI are helpful, but for really precise and dynamic analytics, you need something that goes beyond and gives you more choices. Single imager cameras are generally lower in the price point when compared with narrowband cameras. However, and I'm going to get into this in just a second, the data can vary based on lighting conditions, and that has to do with calibration. They're also usually focused on NDVI, as we've been talking about, and a narrowband camera offers analytics that really go beyond NDVI. Again, before we move on, the broadband imager cameras are often less precise, and the cameras with multiple narrowbands give more options for analysis. So now to get into differentiating and really telling how high quality a multispectral camera is, a narrowband camera. It's important, and we'll touch on each of these, that the data is calibrated, that light sensors are used for calibration, and that it has a certain type of shutter. So remote sensing and multispectral imagery has one limitation of it is that it can be affected by clouds and shadowing because we're measuring reflectance. A plant may reflect more light on a sunny day rather than a cloudy day. So we need some way to account for that. This is what light sensors and calibrated reflectance panels are for, and this is what they do, is that they help deliver a baseline, a control lighting condition that you can compare the rest of the images to and then calibrate from there. Light sensors measure incoming light from the sun and then take data to compare the actual images that are captured with the data that's incoming from the sun. And they're used in conjunction with a calibrated reflectance panel to kind of fine-tune the baseline given by the reflectance panel. They work specifically for what are called global light changes, or changes where they are changes that are the same across an entire field. Light sensors and panels, calibrated reflectance panels, will have a very difficult time correcting for large popcorn clouds, which is a limitation of multispectral imagery, and it's important to know that when you are flying. So kind of the key aspect that calibrated imagery really gives is it allows for analysis over time. It allows you to compare one data set from, say, December to a data set from June, no matter what the lighting conditions were from day to day. It doesn't matter. As long as you have a calibration method and can input that into the processing workflow, you can do time analysis and use of agronomic models. And it's very important, especially for, like I said, this analysis. Something else that's very important is the distinction between a rolling shutter and a global shutter. Multispectral cameras can have either of these. A rolling shutter is similar to the shutter that's in your iPhone. When there's any movement, if you were to shift your hand and either vibrate the camera a little bit or move actual subjects, you'll see waviness. And that's especially important obviously when you're taking images using a drone, because the drone moves and it vibrates. So it's important to have what's called a global shutter, because a global shutter exposes all the pixels of an image at one time and gives you that really clear, crisp image. Global shutters are more expensive, and that's part of the reason why a calibrated camera with a global shutter will be at a higher price point than a narrow or a single imager camera with a rolling shutter. You can, and you always will, get better data, better quality data by using a gimbal and doing some sort of vibration isolation. But if you have a global shutter, the amount of vibration isolation that you do can be lessened, again, because that shutter is a little bit more sophisticated in the way that it exposes the pixels. So before we move on to the next section, calibrated data is incredibly important for temporal analysis or comparing data over time. Without calibrated data, you can't do this, and you will also see different values in whatever indice you're using based on the lighting conditions. If it's an incredibly bright day, like I mentioned before, you'll see higher values as opposed to an overcast day. You need some way to calibrate for that. Light sensors are really an integral part of achieving this calibrated data because they measure what's called ambient lighting conditions, or the light that's coming, shining down on the UAV and shining down on the sensor and down on the plants. Global shutter cameras, as I mentioned on the last slide, are really key for getting good quality images, but also getting good quality data, because there's none of the artifacts caused by vibration or movement. You can get a really crisp, clear image, and then can use that for scientific analysis. So moving on to our next section, I'm going to talk a little bit about the workflow that applies to multispectral imagery. I'm going to focus on some aspects of the flight planning with the UAV, but also focus more on the post-processing side and the analysis side. So when you're planning any type of mission with any type of sensor, it's important to take into account the difference between the area or the field that you would like to be mapped, which is highlighted in green there, and the area that you need to capture. The reason for this is because when you're flying a UAV, it takes some extra time to stabilize after a turn. And if you don't allow for that time and account for that time, then you can have images that are taken at different angles, which make overall stitching very difficult. It's also important to have one extra track at the ends of your field so that you can account for overlap. And I'm going to touch on that in just a second and go into that into more detail. Two key kind of components of overlap as well are what's called front lap, and that's in that left call out there. And that's the distance that images overlap each other from front to back. And then you have side lap, which is the distance that images overlap each other from side to side. So again, overlap, here you see another graphic showing front lap and side lap. Overlap is very important, as I said, to maintain and get the best results. Generally, processing these images, people want, NDVI maps or an Ortho Mosaic, which is all the images stitched together. And to do that, the software and many softwares in general need to find unique components of each image and align those together. If you don't have a high percentage and a consistent amount of overlap, then this can be a problem. And what you can get are artifacts in the data that don't account for what's actually on the ground. So moving to the image processing, after you fly your mission, say with a high percentage of overlap and very consistent overlap, you have two options for processing, two general options. One is a local or desktop solution that's housed on the computer, and you provide resources for that. You do have to do a little bit more manual work beforehand because you need to essentially group the images into projects or group them based on field or farm. You also have to apply a correction for the calibration. So again, just local desktop solutions tend to be more manual. We're going to focus on the cloud solution today because that's what we make, and I have more examples for that. So a cloud solution generally is a little bit more flexible and good for the introductory user because it takes a more streamlined approach. You generally, and I'll talk about this in the next slide, upload and then after a certain amount of time get your outputs back, and there's less organization and less manual work that goes in beforehand. Before we move on to cloud solutions, I will make one note here. For local software solutions, you do want to make sure that the multispectral sensor that you're using is open and allows for you to have access to the raw data that comes off of that. If you don't have this, you will likely have to use whichever software comes with the camera, and that, again, just reduces your flexibility. So just make sure that the sensor that you're using is open and allows for you to have access to that raw data. So moving on to cloud processing, MicaSense Atlas, like I talked about before, is kind of what we're going to use as an example here. But what I'm saying will apply to cloud processing systems in general. So the first part in this processing workflow is to get your raw data to the servers of the platform that you're using. With MicaSense, with Atlas, we use what's called the uploader. It allows you to upload all your data at once. It doesn't matter if the data isn't organized. It doesn't matter if there are calibrated panel pictures mixed in there. You basically just upload everything, and you don't have to do any sorting. So that is just, again, a way that we're trying to make things a little bit more streamlined. And then once you upload, your data is processed and then sorted into farms and fields. And you can create these beforehand. These farms and fields will be, your data will be associated with these based on GPS, the GPS information in the images. And so you can have multiple farms, multiple fields associated with a farm, that kind of a thing. And again, the point here is that you don't have to do any pre-organization. With a local processing system, you would. You'd have to group things manually, image by image, into a farm or into a project. So we'll talk about kind of two aspects of working with the data, quantitative vegetation indices that a lot of cloud processing solutions and even local processing solutions produce, and then also tools that are unique in a way to highlight variation. So in general, any processing platform, after you've uploaded the data, after you've submitted it for processing, will give you outputs in the form of vegetation indexes. Like NDVI, it's a very common one. If you're using a cloud processing system and a narrowband camera that allows you to go beyond NDVI, you can get indices that are more targeted based on the problems that they're trying to correct or trying to, identify. For instance, the chlorophyll map that's denoted here is one that we make, and it's specifically meant to target chlorosis in leaves or leaf yellowing. And again, that's kind of the type of analysis you can do with a narrowband camera, something that gives you more filters than just those needed for NDVI. You can also have an RGB layer that gives you good aerial reference shots, as well as things like NDRE, which is in character similar to NDVI, but is generally better for plants that are more mature. Whichever cloud processing platform you use, definitely do research on what indices they produce, what the outputs are, and what problems those outputs are meant to identify or allow you to see. In addition, a lot of cloud processing tools have visualization, different ways of visualizing the data. In Atlas, for instance, we give you what's called a custom color scale. And what that does is it essentially highlights the, it allows you to customize the way you're viewing the data based on the actual data itself. So if you look down in this left-hand image and see the slider down in that kind of bottom corner, see it's fully maximized. The field looks completely green. There's not a lot of variation in that field, and you kind of look at that and think that, okay, everything's doing pretty well. Well, if you narrow in the slider and display the data in a colorized way based on the actual data that's linked to this graph or linked to this image, you start to see more problem areas, more areas that you could go and scout, and more areas that are lacking health compared to the rest of the field. And that's what, you know, a visualization tool like this really helps for and really allows for. It allows you to get more value out of the data that you have and actually apply it in a way that's useful. Something else that's important, especially if you're using a cloud processing system, like I touched on before with the raw data, you want to have accessibility to the raw data in the end. With MicaSense Atlas, we give what are called Geo Tests. It's like all the raw data, Ortho Mosaic, calibrated, geo-referenced, etc. We give you that in a file that you can download and add your own custom analysis on. This gives, you know, a little bit more flexibility in, again, the way that you work with data. You can use this GeoTIFF in different processing platforms and see what else you can pull out. Something else that's especially valuable with a cloud processing platform over a local processing platform is the ability to view your data from literally any connected device. You can walk your field looking at a laptop, looking at a tablet, looking at your data and do very targeted scouting based on what you see on a crop health map. And this, again, really highlights how this information is not just pretty pictures, it's data, and it can be used in a way to create tangible results. So before we move on to this last little section, I want to hit home on a few things. One is going back to that, that piece about flying your mission. It's really important with multispectral cameras themselves to fly with consistent overlap. Specifically 70% is kind of a good guideline. It yields the best results. It will give you an artifact-free data set. Local processing also allows for manual customizable analysis. It does require more resources and time, but for someone who wants to have control at every step of the way and for someone who really wants to dive deep into their data, this is a perfectly viable option. For someone who wants a more hands-off approach and wants to be able to press a button and have it be done, a cloud processing solution is generally focused on ease of use and offers, you know, completely standardized outputs, and it allows someone who doesn't have the familiarity with image processing to use the data in the same way. Just some key things to consider when evaluating software solutions, more from a business standpoint. It's important to know what will really suit your business case. So, you know, how is your internet connection? Is a cloud software realistic? Does the software platform work within your target vertical? You know, especially if you're doing agriculture, it's important to make sure that the processing platform has agricultural features and is targeted for that vertical. And then what features really give the most value to your customers? Again, if you're approaching this from a business standpoint, will they want to know will they want to see Ortho Mosaics? Will they want to see crop analysis? Will they place a high importance on a fast turnaround time? Do they have their own software that they want to input this type of data into? Moving on to data applications, I'll talk a little bit about how this data can actually be applied. In general, multispectral imagery can be used as a spatial detection tool. You can see here in this image, the trees that are depicted in red actually have a specific disease called Phytophthora. And what the grower was able to do is he was able to use this map, it's an atlas map, to target these trees and go in ground truth and remove these trees before the disease spread to anything else. Again, especially a value not only with the processing platform that gives you multiple analysis options, but a camera that allows you to do multiple different indices. This is actually the chlorophyll map that we produced, like I mentioned earlier. It's not NDVI. This type of disease was not visible in NDVI. So as a spatial detection tool, you can do early detection of disease as I mentioned here. You can look at the effects from a pest infestation. You can look at certain types of, at the effects of weeds that are coming through, as well as general crop health monitoring. In addition to that, this type of imagery can be applied as a farm management tool. It can help inform a grower's decisions on when to apply fertilizer or how that fertilizer is applied. Here in this image, if you look in the center, one of the center rows, you'll see some yellow striping. And that's actually because of a spigot that was broken. And what it meant is that fertilizer was not applied in a consistent way. And because the grower was able to see this early on and detect this change, he was able to adjust and correct and fix the spigots and make sure that this didn't have an overall impact on the yield. This type of tool also goes towards helping farmers understand when to harvest based on maturity, and also, as I mentioned, helps people understand where the variability in the crop yield could be. So, while especially the applications sound very exciting, and this is, it is very, very exciting technology, there are considerations that are important to remember. Field scouting will always be necessary with a tool like this. This isn't going to specifically say this tree has this disease. It's going to say that this tree looks unhealthy, and it gives you a location to go scout from. There are a lot of solutions on the market right now that are generated from non-scientific data. And it's really important to remember and understand the source for some of these solutions, like prescription maps. What is the sensor, the camera that was being used to generate the data that was then generated for a mapping or a prescription map, the fertilizer prescription map. It's always important to kind of come back to the science and understand that if there isn't a significant scientific grounding, then this data is really not going to have a tangible result. Something else to know is that high spectral resolution is very different from high spatial resolution. So a camera with a high spatial resolution might be a high resolution RGB. Those are great for generating an elevation model or a point cloud. This type of camera, a multispectral camera, while it has a red, green, blue filter, red, green, blue band, it's important to make sure that you're using the right tool for the job. A multispectral camera with a red, green, blue band may not give you the type of resolution you need to really come up with a digital elevation model. So again, consider what the application is and consider what type of camera sensor you really need. So what is really exciting about this is that right now, agricultural UAS technology is helping to monitor and manage crop health. It's helping to counteract early detected issues during the growing season so that farmers can make decisions mid-growing season and recover from a disease that potentially could have wiped out the entire crop. It's also helping to minimize labor and time to scout, the entire field. With this type of technology, people can find pinpointed areas where they need to scout, as opposed to walking up and down 300 acres of grapes or corn or that kind of thing. Really, the future of all this, though, is the ability to integrate this data and this type of system into other connected systems and, again, create a database of information that a farmer can leverage in a complementary way. Going back to that graphic I showed early on, multispectral imagery and remote sensing data needs to be used in ways that are complementary to the rest of the tools in a farmer's wheelhouse. It's not the end-all, be-all solution. In conclusion, to kind of tie this all back together, really the value is in the data. Good quality data that can be applied is going to have the biggest impact on and create the most tangible results in general. Calibrated narrowband cameras give high quality, precise data. And they also allow, as I mentioned before, that analysis over time that gives you more options for NDVI. In the example I mentioned earlier with the trees that were affected by the disease, that isn't visible in NDVI, and it needs
it looks like we're having a little bit of technical problems. Alyssa's audio just dropped, but we're going to try and get her back. Everyone can just bear with us for one moment here.
Uh-oh, can you hear me?
Yep, we can hear you now. Dropped off for a moment there.
Oh, goodness, I'm so sorry about that. I don't know what happened. Where did you last hear me?
You were on point number 2 talking about the NDVI.
Oh, okay. Yeah, just kind of, something I've been mentioning throughout the presentation, that the analysis that goes beyond NDVI is really of value and is becoming more and more valuable in the industry. Like I mentioned earlier with the example with the trees affected by disease, that's not something that could be seen in NDVI. You need an index that takes that analysis further and highlights other variability in crops. In addition, the data analytics, as I mentioned before, really need to be customizable and need to help farmers carry out targeted scouting and actually see that result and feel like the data is more than just pretty pictures and that they can use that in a valuable way. And that's it for our presentation. So thank you so much for listening. And I'm going to open it up to Q&A. Katie, do you want to mention anything or?
Yeah, absolutely. First of all, thank you, Alyssa. That was great. So like she said, we'll switch to Q&A now. You can submit your questions using the chat box on the right side of your screen, which is down that right corner. So go ahead and type the question in and then hit the send button. We have a few that actually came in privately while you were speaking, Alyssa, so I'll go ahead and get started with those. The first is, what are the optimal altitudes to fly at for multispectral sensors?
Multispectral sensors, especially any drone-based sensor, will work at multiple different altitudes. Generally, we recommend with our products that you fly as high as possible, so at 400 feet. However, you will get better resolution if you fly lower. You'll collect more data, but sometimes resolution is important. So anywhere from 50 feet to 400 feet is completely fine.
All right, thanks.
And then,
the next question, go ahead.
No, go ahead.
The next question is, many articles speak to repeatability with regards to data. Can you speak to this with regards to NDVI versus narrowband cameras?
Yeah, of course. Repeatability is, again, something that we are really, really focused on. You will get repeatability if you have a calibrated sensor. That is something that is very, very important. NDVI produced from a non-calibrated sensor generally won't be repeatable. You won't see the same NDVI values from day to day just because of that, that effect from the sun and from the different lighting conditions that I talk about. So yeah, calibrated imagery for repeatability completely.
Great. Next up is, because you use multiple overlapping images to create Ortho Mosaic maps of NDVI or other vegetation indexes of farm fields, which particular one of these images do you use to calculate the vegetation index value for any given pixel in the resulting map?
So we Ortho Mosaic all the images together first, and then calculate NDVI after all those images are mosaic together. Again, for specific technical details, we can have a private conversation, but in general, the general approach is to mosaic all the images and use their reflectance values in each location after the mosaic is created to generate that NDVI value. And it, again, depends on the resolution as well.
Okay, great. Now we just have a few more product-specific questions. So the first one of those is, do all MicaSense Red Edge cameras have a global shutter?
Yes, all cameras that we produce, so which is just the MicaSense Red Edge, has a global shutter on all 5 lenses. So every image that comes off of that camera is taken with a global shutter.
Okay, and then what drone systems has the Red Edge been integrated onto, and how hard is it to integrate on a Pixhawk autopilot?
Yeah, so from a platform perspective, we are drone agnostic. The Red Edge is very simple to integrate onto most UAV platforms. It's got mounting points that really lend itself for that. And then from a software perspective and kind of an electronical perspective, the Red Edge uses industry standard communication protocols. Again, getting a little bit into the technical aspects here, but it uses what's called Mavlink. And that is also what the Pixhawk communicates over, and you can get those to talk to each other. We have a lot of customers that do that.
Okay, great. And then does your sensor stream data in real time?
The MicaSense Red Edge, no, it does not. It stores all the information, all the data to the SD card, and then afterwards you pop out that SD card and process the images that way. We don't have a data streaming option. Okay.
So earlier we talked about the optimal altitude for imaging. Is there an optimal speed for the drone to fly? Does it need to hover? Can it go pretty quickly for this to work?
Yeah, of course. What kind of the limitation there is the capture rate of the camera. So whichever camera you're using, they'll have a specific time or kind of the limit on the time at which a picture can be taken. Like a lot of cameras can only take 1 image per second. So you have to make sure that your drone is flying slow enough to account for that. So for like the MicaSense Red Edge, for instance, you can fly as fast as 15 meters per second, even faster if you're at a high altitude. If you're at a lower altitude and the camera is set to trigger, once every second, you need to make sure that you're flying slower so that capture rate isn't maximized.
Okay, thank you. And then we have a couple of questions now from specific use types.
Yep, no
the
problem.
first one is, does the farm size matter when using this type of technology? Do you need a larger farm to get good data points?
No, you can have any farm size you want, any field size. I think kind of the limitation there is that do you really want to be flying a 10,000-acre farm with a UAV? That's something to consider. A lot of our customers are flying fields and farms that are anywhere from 1,000, 1,500 acres, depending on the capacity of their drone.
Right, that makes sense. The next question comes from a listener who works with timberland owners, and he's wondering if MicaSense has worked on any sustainable pine forest projects, or if you know of your products being used in that way.
We do have a few customers who are flying over forestry. I don't know about pine specifically. I know that they're flying over in British Columbia, flying over forest there. It's definitely something that the cameras can be used for. It's totally a viable application. And it's something, I mean, from a sustainability standpoint, something we would love to get involved in.
Great, thank you. The next question is, any work on how to increase the wavelength of the cameras to identify other information? This listener used to work with optical sensors for oil and gas analysis, and they would detect water picks and CO2, that sort of thing.
Yeah. So right now, with the red edge specifically, the wavelengths and the filters that it uses are meant to specifically detect changes in a plant's health. Their locations, I showed it on the slide, are specifically meant for that. We may make other cameras in the future that have filters that are designed to detect other things, but right now the camera and the filters itself are focused on the curve of a healthy versus stressed plant, and that's kind of where they'll stay. We like to engineer all of our cameras without any moving parts. That's why our filters are set and done, and that just helps on the ruggedness of the sensor. We don't want to have anything where you can interchange filters and interchange lenses because, again, it goes back to that repeatability. If things have moved around, if the lenses have moved around, then you don't have as much repeatability from the sensor standpoint.
Okay, thanks. The next question is, how are your sensors powered? Yeah,
of course. So the MicaSense Red Edge is powered by an external source. So you can set it up with a battery elimination circuit or a DEC to pull power from the UAV's battery, or you can use an external battery pack like a USB battery pack or something to power it. But yeah, I mean, we try and give as many options as possible. The UAV option is generally what most people go with, because it reduces weight.
Great. Can a multispectral camera tell you anything about water stress?
Yeah, so a multispectral camera, again, is just meant to highlight the changes in a plant. And for anything that kind of has to do with water and temperature, we definitely recommend going with a thermal camera as opposed to a multispectral camera. A multispectral camera could show you that a plant was less healthy, but it couldn't specifically say because it was stressed. It was due to water stress.
Okay, thank you. We have a couple more minutes, so we'll try and get in one or two more questions, but I just want to reiterate for everyone that we will be sending out a recording of the presentation next week. You'll be able to come back and visit this later. So the next question is, what outputs do farmers specifically want in regards to this type of data?
Yeah, I mean, farmers want anything, and I can't really say that we can speak for all farmers here, but what we get requests for the most are outputs that can be applied. So people really want, prescription maps and that kind of a thing. They want NDVI maps that talk about their health, the crop's health overall. And that's something that, we're really focused on providing, are things that actually meet a need and a focus of the farmer, things that are targeted to actual problems that they face on the ground.
Okay. The next question is, are your sensors ITAR restricted?
No, they're not.
Okay, thank you. Earlier you mentioned a 70% coverage. This person is asking if you could expand on that a bit. Does that mean that you overlap 70% of the previous task?
Yeah, yep, so kind of generally. What the 70% overlap is referring to is that you want two images that are either right next to each other or before one another and after one another. You want at least 70% of I guess overlap is the only way to put it, between those two images. So you want them to have each one with 70% of the image that's the same as the other one. And that's, again, really important just so that the reflected values that are being measured can be stitched in an accurate way.
All right, great. And then the last question is, you talked at the end a little bit about the future of farming, but if you had to jump ahead 5 years, what does precision agriculture look like? What are the biggest differences, and what sort of technology are we using?
Yeah, of course. I definitely think that the drone is going to play a really huge role in that. I mean, UAVs have the ability to carry different sensors, not just multispectral sensors, and they can really help farmers get a holistic view of what their fields and what their crops are doing. I also think, like I said, that the incorporation of different data layers, soil mapping, weather information, fertilization information, changes in elevation, that is really going to be key, because in reality, all of that comes into play. All of that is a factor when determining plant health. It's not just, water stress. It's not just soil type. It's everything. And so if you can look at that from a holistic perspective, and that's really, that's where we see the market is going, then that is kind of the key.
All right, thank you. So now we've reached the end of our session for the day. On behalf of AVSI, I'd like to thank Alyssa, Ryan, and Micah Sense for their support, and thank everyone in the audience for your participation as well. You'll all receive a link to access the webinar recording within the next week. And be sure to visit our website, www.avsi.org, for a complete list of upcoming programs and services. If you have any additional questions or comments, please contact me at kcooper@avsi.org. Lastly, today's program is copyrighted by AVSI with all rights reserved. Thank you, everyone, for joining us, and have a wonderful afternoon. You may now disconnect. Alyssa, thank you so much for joining us, and Kelly, thank you also for all of your help leading up to this and getting us all organized.
Yes, of course. Thank you so much.
Really well.
Yeah, really appreciate it.
Yeah, and I'll be sure to get you all the list of attendees and that sort of thing in the next couple of days.
Okay, cool.
All
yeah,
right.
thank you.
All right, thanks so much.
Yep.
Have a good one.